The reality is sets are fun because there is a general sense of it. What we're talking about is just a collection of objects, right? And sets specifically are an unordered collection of objects. So far, we've talked about primitive types of objects, so numbers, booleans, um, really basic things. But now we're going to get a bit more complex because we're talking about all of those things, but we're looking at the collection of them. So when we talk about collections of them, they come in two varieties, and we'll see them both between this class and next. And that is unordered collections, and those are sets, and ordered collections, which are sequences. And I've already used the word sequences because sequences are something you've seen in mathematics, but we're going to be more formal about how we describe sequences. So unordered collections are what are of interest to us right now. So a set is an unordered collection of objects. Okay, well, I didn't tell you what kind of objects. And I did that intentionally because a set doesn't care. It can be a set of students. So it can be a set of bits. We learned about bits, and the bits are only come in two forms, 0 and 1, right? And so we can talk about the set of prime numbers, which we spoke about today, 2, 3, 5, 7, 11. Fun fact, that never ends. And we can prove that later, and we will when we get to proof. Uh, the set of even prime numbers, that is finite. That does end. There's only one even prime number, and it is the number 2. And we talked about that because 2 evenly divides all other even numbers. And so all of the rest of the even numbers, positive even numbers, are composite. I've specifically listed the prime numbers in order. That's for me. Um, but the reality, and I listed the bits as 0 and 1, but the set 1, oh, I don't like writing in red for this, but we'll do it for now. So the set 1, 0 is the same as the set 0, 1, and that's because the order doesn't matter, right? This is an unordered collection of objects. The order doesn't matter. Okay, the set of two-digit perfect squares, 16, 25, 36, 49, 64, and 81. So those are all the two-digit squares. So taking an integer and squaring it. So that's 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, and 9 squared. Any other perfect square is either a single digit or more than 2 digits. These are all of the two-digit perfect squares. If I mess those up in a different order, I'd still have the same set of numbers. Okay, so yeah, of course. So we can also have other sets. So sets aren't limited to integers. We are going to play with a lot of integers at times, but you all form a set. You're an unordered collection of students, right? If we look through the list of participants, that is a set of students in this class. You can have a set of arithmetic operators, plus, minus, multiplication, and division. You can have the set of all the integers, that double stroke Z that we learned about last class. You can have the set of the real numbers, the set of the rational numbers, Q. Okay, all of these are sets, and all of those can be also modeled and used within programming languages. What does it mean to be a member of a set? It's something that we can define in this class. If you're registered for CSCI 1315, you're a member, an element of the set of students in this class. Okay, so to be a member of a set, and we'll call the set S, and an object X in that set, X is said to be an element or a member of that set, and we denote it, meaning the way that we represent that is writing X, and I say X in S. That's how one says this little symbol. But X is in S if X is one of the objects contained in S. You are an element of this set. You are an element of the set of students in CSCI 1315 because you're one of the objects in that class. Okay, so we say X is in S, and there's also a symbol for something not being a member of the set. So I happen to know that Brent is a TA for this class, but he's not a student in this class. And so So Brent Crane, unfortunately, is not in S. And we would represent that by this symbol, the same symbol with a line through it. That's just X is not in S. Okay, we also talk about the cardinality. So how big is a set? And this is something that you'll use when you look at arrays in Java, right? You're going to find the size of the array. The cardinality of that array is what you're actually obtaining. And that's denoted by these pipes. So we would always write it as follows, and that is just the number of distinct elements in S. Okay, so the number of distinct elements in a set. And so if I look at the set of bits, right, 1, 0, 0, 1, doesn't matter how I represent that, there are two elements in there. And so the cardinality of the set of bits is 2. If I look at the cardinality of the set of 2-digit perfect squares, which we've already defined as 16, 25, 36, 49, 64, and 81, sorry, 1, 2, 3, 4, 5, and 6. So it's yeah, 4 squared through 9 squared. There's 6 of those elements. The cardinality of that set is 6. Okay, so this sounds super easy, right? This is just counting. I underlined it for emphasis, but this is a trivial thing. It's just counting. We'll just wait for it. This is not as easy as it sounds at times. So in the examples I'm going to give today, counting is really easy. But how many integers are there? Count them up for me. um, in fact, there's an infinite number of them. They never end. And then, well, how many non-negative integers are there? Actually, they're the same number of non-negative, or even pick one, negative integers. They're the same number of negative integers as there are integers. How is that possible? There are more of them. It's only like, other than 0, that's like half the set. How is that possible? Counting is not as easy as it sounds. And there's a whole section, a module of our work that gets to counting. And it's difficult enough that it's the last 3 weeks of our course. So as trivial as it is for these simple sets, it gets really crazy. And in fact, it gets quite fun. So there's a whole area that looks at this. In fact, okay, here's one of my favorite examples is um, you can use similar ideas. Oh, also, well, anyway, I love the area of counting. And so start thinking about the number of even numbers versus the number of odd numbers. Should they be the same? Should they be different? What about the number of integers versus the number of real numbers? Should that be the same? It'll make your head spin. When I was a kid, I used to have literally nightmares about the concept of infinity, and I just think it's so amazingly brilliant now. So there's similar ideas when we talk about like the complexity of this counting have been used to prove that there are fewer computer programs than there are problems to solve. Okay, so what does that even mean? So some problems are not solved by any computer. And this is a central idea to a whole area of computer science, which is about computability and non-computability. Can we use programs to do this? Or, yeah, has it already been done, essentially? Good fun. The summary for that is counting is not always easy. Sometimes it is, but it's not always easy. And we'll make it easier as we go forward. Oh, and there's the fun fact that I already gave, is that the cardinality of the set of integers is the same as the cardinality of the set of those integers 0 or greater, which feels wrong, right? But we'll prove that that's true at some point.